Swayam Prabha. Digital India. Educated India.
I come from the Environmental and Water Resources Division. My research is focused on water security, food security, climate change impact on food production, stuff like that. Before we go and talk about the global hydrological cycle, I wanted to give some feel for numbers for a small flower pot here. Whatever processes happen at the flower pot also happens at the hydrological cycle on a global scale. But it's there are a few complications in terms of heterogeneity and a few other things. We'll go step at a time. But let's say we have a flower pot and then we have some rain or we water it, okay. So that's our precipitation, which is the input to the system, okay. And then the water, if you pour very fast or too much water, it'll fill the pot, it'll spill over and it'll overflow. So that process is called runoff or stream flow. So that's what happens in the earth also. When you have a lot of shower, the earth cannot absorb it, it'll start ponding and it'll start flowing off, runoff. So that's your runoff. Some water actually goes inside, it infiltrates into the soil, okay. And you have soil moisture and you have groundwater. So you have infiltration process where you can have saturated, unsaturated soil moisture. Also if you go further deep, you have your groundwater which is saturated. And then groundwater actually flows based on gradients. So you can have some regions which are higher, some regions which are lower. And then if there is saturated groundwater, water flows from higher head to lower head. So you will have regional groundwater flow. In our flower pot, we have leakage. So we have all planting pots have some hole in the bottom to let for drainage. So we have leakage or drainage at the bottom. Now we also have evaporation from the surface. So you have bare soil. Some portion of the flower pot has plants, some portion of it has bare soil. So you can have bare soil evaporation based on your sunlight, temperature, humidity and things like that. You will have different rates of evaporation. And finally, the basic reason we are pouring water for a flower pot is for the plants to uptake water. So plants actually use water. It's not evaporation, it's called transpiration. So the process by which water goes from the soil through the plant and then comes out of the leaf is called transpiration. So together there are two fluxes that go out into the air, okay. So one is evaporation directly from soil or water bodies escaping into the air, so that's evaporation. The other is transpiration, which is flowing through the plants. And then two, which is liquid water, you get runoff at the surface level or you get groundwater flow at the subsurface level. So basically this cartoon kind of gives a feel for what are some storages, what are some fluxes that we can expect at a small watershed or a flower pot, okay. So now let's scale this up to the global level. So we have now a global hydrological cycle. There is this spatial and temporal scales are much larger, okay. So now we have evaporation. Evaporation not only happens from the ocean, okay. So it also happens from the land masses. There is lakes and rivers where surface evaporation can happen. And there are plants and vegetation, forests, grassland, all kinds of ecosystems which transpire water. So there is going to be large scale transpiration which is releasing water in the form of gaseous water vapor back into the atmosphere. You have precipitation. So we are used to having precipitation in the land, but we also have precipitation in the ocean. Water can precipitate in oceans also. In fact, more portion of water that falls as rain falls in the ocean than in the land, okay. So that's your input, and you can not only have precipitation in terms of water, but you can also have precipitation in terms of snow, hail, sleet, different kinds of things. Now, then what happens to the water that falls on the surface? So once the water reaches the surface, it can either pond, it can collect into lakes, it can flow in rivers and have some surface water flow. So these are your rivers and small streams and creeks that flow on the surface. So that's your surface outflow. You also have water that's infiltrating deeper into the soil and it becomes part of the groundwater. And now you have a regional groundwater flow and eventually all the water kind of goes into the ocean, right. So you have a cycle. The reason it's called a cycle because you have evaporation from the ocean and then precipitation back into the land and then flow over the surface or under the surface and then emptying it out into the ocean. You also have evaporation and transpiration that goes back into the atmosphere. So there is a big loop, there is a big cycle. Now the question is, at what time scales these are happening, or what are the magnitudes of flows and what are the magnitudes of storages. Can we put some numbers in this and see what happens? So let's see in terms of storages. If you want to say, let's say this is on an annual time scale, let's say we have steady state, like interannual variability is low. So on an average, we want to see how much water is stored in different portions of the hydrological cycle. So now, when we look at the ocean has about 1.4 million cubic meters of water. So 1.4 million cubic meters of water is stored in the ocean. It's the largest reservoir in terms of reservoir storage. So then there is some amount of moisture that is stored in the atmosphere. So this is your atmospheric water vapor. So when you talk about humidity and things like that, there is water vapor stored in the atmosphere. And this, it is here we have split into two parts, the portion of water vapor that's stored in the atmosphere on top of the land, and then the portion that's stored on top of the oceans. So obviously you have more evaporation happening on the oceans, so you are having a little bit larger proportion of moisture stored on top of the ocean atmosphere. So then we have a large amount of water, about 43,000 cubic kilometers, stored in, locked in ice caps, okay, as snow and ice and things like that. And then you have a fairly small fraction of that as freshwater storage in lakes and surface waters, okay. And another significant portion of storage is in your groundwater, about 15,000 cubic kilometers. So this whole flux on an average, on an annual average scale is kind of, there may be some variability between year and year, but overall these are the numbers that you can think about. So now this is the storage. Now what about flux? So there is always exchange of mass between one reservoir and another reservoir. So for example, what do I mean by reservoir? So there is a reservoir of moisture in the air, in the atmosphere. There is a reservoir of moisture in the ocean. There is a reservoir of moisture, let's say, in lakes. So they are constantly interacting and they are exchanging mass. So for example, a surface water or subsurface water, which was in liquid form, is now being transpired through the plants or evaporated and put back into the atmosphere as soil moisture. So how do these things interact? What are the rates of change of interaction of mass flux between these storages? So here are the mass fluxes in terms of kilometer cube per year, and they are highlighted in red. So let's see, from the ocean, we have about 505 cubic kilometers per year of moisture that escapes from the ocean as evaporation and gets put back into the atmosphere. And of that, about 458 kilometer cube per year falls back into the ocean as precipitation. So significant amount of ocean water that evaporates actually comes back as precipitation into the ocean. Some of it gets carried, about 46 cubic kilometers get carried back inland, okay, as moisture, and this 46 comes back into the ocean. So you see 45 as surface and 1 as groundwater flow comes back into the ocean. So between land surface and ocean, you have 46 cubic kilometers per year that goes from ocean to the land as water vapor, and about 46 that comes back as water. So then once you get into the land atmosphere, so you have evaporation and transpiration coming from plants. It's about 73 cubic kilometer per year. Combine that with the ocean contribution, so you will have about 119 that precipitates back into the land. And so some of it infiltrates, and then you have surface runoff and you have groundwater flow. So among these you can see your groundwater flow flux is fairly slow, whereas your fluxes in the atmosphere are fairly fast. This is in terms of fluxes, but if you look at in terms of storages, your storages in atmosphere are very small, right? You have about 15 cubic kilometers, your storage is very small, whereas your storage in groundwater is 15,000 cubic kilometers. So there is a huge discrepancy between the magnitude of flux that you see as storage and the magnitude of flux that you see as, magnitude of volume of water that you see as storage, and then the magnitude of flux that you see exchange between these reservoirs. So as a result, what do we get? So let's do some mass balance, okay? So in terms of land surface flux, so this is just recap of what I said earlier. So if you just take land surface, the rate of change of storage of soil of moisture in the land surface is equal to sum of influx minus sum of outflux. So I say on an annual scale, things are balanced. So flux is 0, rate of change of storage is 0. So your net flux is also 0. So there are inputs and outputs. So here I have put 119 as input and 3 outputs, 73, 45 and 1. So let's go back to the previous slide and see what we do. So we have so basically I'm trying to do a mass balance for this surface. Okay. So this is the land surface. So 119 is the input, that is this precipitation, and you have 73 as output here, 45 as output here as surface runoff, and 1 as groundwater. So you can also similarly do your ocean mass balance. So quickly let's go back to the previous slide. So before we go there, so rate of change of storage ocean. So basically ocean, don't talk about sea level rise here, but on an average, let's say ocean fluxes are kind of storages are pretty much stable. So you have three things that are going in, 45, 1 and 458, and one thing that is going out, 505. So let's see what are these fluxes. So 505 is the evaporation from the ocean, that's going up. 458 is precipitation, whatever water that evaporated is precipitating back into the ocean. So that's about 458. 45 is surface water flow and 1 is groundwater flow. So on an average, things seem to be balanced. Now, so I was earlier mentioning about the consequence of difference in magnitude between your storage and fluxes. So let's look at groundwater. Your groundwater storage is about 15,000 cubic kilometers, whereas your flux is only 1 cubic kilometer per year. So we can compute some kind of a residence time or detention time. So you divide your storage over your flux, so you'll get an average estimate for how long a water molecule kind of stays inside the groundwater. So that comes out to be about several thousand years. So that's typical. If you look at groundwater velocities, if you don't have any severe pumping and some man-made artifacts, naturally water flows fairly gently because there's a lot of resistance. You have to move through the soil, you have to move through the porous media, and gradients are fairly less, not very steep. So your water moves at about few meters per year, few tens of meters per year. So considering the global scale, it takes about 1,000 years for water to on an average, thousands of years for the water to move through the groundwater system. Whereas if you flip it and look at the atmospheric storage, so let's go back to the atmospheric figure. So you have fluxes, your storages are fairly small. So you have 4.5 and then you have 11, but your fluxes are very high, 119, 46 and 73. So in this example, I have looked at 45 plus 11 as a total atmospheric storage. Your fluxes are total incomings 458 and 73. So there's a huge amount of flux that puts water back into the atmosphere for a very little storage. As a result, your detention time or residence time is fairly low, and that's kind of few days, so about a fortnight. So they say weather systems kind of last about 2 weeks, 1 to 2 weeks. So this is where it comes from. So the time that water stays in the atmosphere is orders of magnitude smaller than how long it stays, let's say for example in the groundwater. So I'll leave this as an exercise for you guys. Why don't you do a quick calculation for what the surface water storage will be and what the surface water flux will be, and so how much will the residence time be. So maybe you can do a quick math. So your fluxes and storages. So storages are in the black and fluxes are in red. Now can someone tell me what numbers will we get? So you want to do a mass balance. So mass balance is, we know that the mass balance is satisfied, so there is no rate of change of storage. So you are trying to get storage over flux. So without doing calculation, what is a typical residence time that you would expect on the surface? Will it be order of thousands of years, or will it be order of 1 or 2 days, or will it be kind of in between? In between, okay. So what is your estimate, guesstimate? About 100 days, good. Who else, so what is your name? Anirudh, so who else agrees with Anirudh? About 100 days, it sounds about right, so we have quite a few people. Anybody has some other estimates? Okay, so we have, it's not way off, so you can do the math, it's several hundreds of days. So around 100 days is not a bad number. So when you think about, storing water, if you want to store water in your surface versus if you want to store water in the ground, you think about what water is more accessible or, more easily retrievable. So it's probably if you store it in the ground, it's not moving very far away, and it's there for a long time. You're not occupying space and additional space in terms of surface. You're preventing evaporation, and water moves fairly slowly in the subsurface. So there are advantages to recharge groundwater. Okay. So we talked about these numbers. So 1 cubic kilometer. I mean, what is this 1 cubic kilometer? It's some number. I mean, how big is it? How small is it? We are talking about global scales and we are trying to move water. I wanted to get want you guys to get some feel for some numbers here. So what is 1 cubic kilometer of water? How much is it? So let's say, typically I want to think in terms of swimming pools. Like let's say an Olympic sized swimming pool has about 2,500 meter cubed of water. So 1 cubic kilometer is like 400,000 swimming pools. Like that doesn't really help. Like how can I visualize 400,000 swimming pools? Like not able to get a feel for the number. So can we come up with some other estimate? Okay. So let's say we take IIT campus. It's about 2.5 kilometers squared. Now I want to put 1 cubic kilometer of water on top of this IIT campus. So which means you will have about 400 meters of water all over the campus, and that will constitute about 1 cubic kilometer of water. So what is this 400 meters of water? 400 meters of water. How tall is it? So it's about 130 floors. Like if you have a building, it's about 130 floors. So that amount of water is 1 cubic kilometer all over campus. So this whole 2.5 kilometer square area, you fill it up for 130 floors of water. So that's 1 cubic kilometer. You get a feel for the numbers. It's really high. It's huge. Really huge number, right? So what's the tallest building in India? Does anybody know? Anybody know what the tallest building in India is? Yes? Can you be louder, please? So the tallest building in India, at least according to Wikipedia, is the 42. So it was recently constructed. It's about 260 meters. So about 65 floors. So it's actually taller than the tallest building in India. The amount of water, we have to stack it up, is much taller than the tallest building in India. This is a really huge number. So when we throw these numbers around, and we say like 500 cubic kilometers of water per year, it's a large amount of water that is being moved annually. Okay. So let's say in terms of annual average precipitation in Chennai, so it's about 1.4 meters, so about 140 centimeters. Every year we get on an average around this area. Okay. So how many years does it have to rain to get 400 meters of water? So it's about 285 years. So if it rains for 285 consecutive years and every drop of water is saved, okay, that falls on campus is saved, and that amounts to 1 cubic kilometer. It's a really huge water, huge amount of water. So I'm going to go back to the next slide and let you get a feel for the numbers. Look at these numbers and just soak it in, see what the storages are, see what the fluxes are, and in relation to your 1 cubic kilometer of water, which is about 400 meters of water all over IIT campus, get a feel for these numbers. So, it's very hard to think about 500 cubic kilometers per year is being evaporated from the ocean. It's a really large number annually, every year. So, now let's go from global scale to more manageable scale, let's say a catchment scale or a watershed scale. So, we looked at fluxes, at the global scale. Now let's see what kind of fluxes happen at the catchment scale or at a more manageable scale. So here is an example of a catchment. Okay. So the green highlighted region is actually the catchment area. The red line is the catchment boundary or watershed boundary, and the bottom of the red line is a watershed outlet. So what do I mean by watershed? So I have identified in a map. So this is a topological map or elevation map. In this map I have drawn a line, a red line, and I have said whatever water that falls in is going to come out in this watershed outlet. Okay. So basically I have delineated a watershed based on a topological map or elevation map, and I say that if a water falls inside this map, okay, inside this green region, it is going to drain out at the watershed outlet. So how do I determine this watershed boundary or this watershed divide line? So somebody said slope. Yeah. So how do you determine based on the slope? So it's a hunch you have based on some slope, but it's basically based on elevation. Okay. So it's based on elevation differences. So let's say we have a picture here. So typically a watershed boundary is defined as a ridge line. So how many of you know what a ridge line is? Anybody ever heard this ridge line before? No? So what you're seeing right now is a ridge line. Okay. So there is a hill, so there is a series of hills, and so the highest point along which you can draw a contour is a ridgeline. Okay. So any water that falls on this side of the ridgeline is going to go to my right, and any water that falls on this side of the ridgeline is going to go to my left. So this is a watershed divide. So basically any precipitation that falls to the left is going to go left side, and any precipitation that falls to the right is going to go right side, and they are not interacting. And so a ridge line is a typical watershed divide, and it defines your watershed boundary. So your watershed boundary is watershed is where area is where if you have precipitation falling on that defined area, you are going to have one particular point which is your watershed outlet where all the water is eventually going to drain. So you get a good feel for how you identify this ridge line pictorially, right? So here is another ridge line, so I'll go back. So here is another ridge line right here. I mean, there are many ridge lines. There is another ridge line here. Any water that falls here is going to drain out this way. Any water that falls on behind the slope is going to drain away from it. So now, how do we get these ridge lines? So obviously you need elevation maps. So you can't really do aerial, like land surveys and go and track ridge lines and then map them. So we have sophisticated ways where we can do this. And so one system that helps us do this is geographic information systems. Okay, it's also called GIS. So it's a system that can manipulate, store, arrange and process data which are spatial in nature or geographic in nature. So they have some relation spatially, some correlation spatially is your geographical information system allows us to do. So here is a digital elevation map. So your red colors or darker colors are corresponding to higher elevation, your blue colors are corresponding to lower elevation. So you can see that you can see your low points and high points based on this digital elevation map. Now from this map, how do we get your watershed boundary? So I want to know what is what the use of watershed boundary is. You can kind of think of it as a unit which is separate in itself, that is not interacting with your neighboring boundary. So whatever precipitation that falls inside this watershed is kind of its own unique unit, and what falls outside the watershed is not going to influence directly the processes that happen inside the watershed. So now, if I want to study a part of your area, and if it has many different watershed interspersed, like I can put a, let's say I put a solid block square rectangle here and say I want to look at the water fluxes in this area. So then you are going to have fluxes that come through the surface, right? So on either sides of your boundary, your artificially defined square boundary, you will have fluxes coming in. But if I choose my boundary as a watershed boundary, then there are not going to be any horizontal fluxes that come through the watershed boundary, because as we saw earlier, any water that falls on the left is going to go this way, any water falls that's going to fall on the right is going to go the other way. So there is no cross flow of water across a divide. So how do we find this watershed boundary? Using your digital elevation map. So your GIS systems, geographical information system, allows us to do that. So let's do some quick math. Okay. So what your digital elevation map does is it's a raster of points, it's pixels. It has different pixels, and each pixel has a particular value, and that value is, let's say, elevation above mean sea level. Okay. So here I have a small section of your digital elevation map, small snippet of that, which has height above sea level, mean sea level at different points. So now you have your cell size. Now here I have conveniently taken my horizontal and vertical cell sizes to be equal, but in general you can have unequal sizes. Okay. So now this is your DEM, which is what I have projected as a color plot in this slide. So now, how do we determine from this DEM your catchment or watershed boundary? So first thing is you try to find which direction your water flows, and the best way to do this is to find which is the direction of steepest descent. So from point A to point B, so each point has 8 surrounding points. You find out which direction is your steepest slope, and that is the most likely flow of water. Okay. So now for the top cell, the top left cell, the elevation is 67. Your adjoining cells have elevations of 56, 44 and 53. Now if you want to compute the slope this way, okay, so then you do 67 minus 53 divided by 1. So 1 is, let's say, 1 kilometer or something like that. It is a unit and it is uniform. So you take from this midpoint to this midpoint, it's about 1, and so you get slope as 14. Whereas if you do diagonally, so then you have to do square root of 2 because it's in this case it is symmetric, so you do a square root of 2 and you get a slope. So similarly, you compute the slope at different directions and then you pick the steepest slope. The steepest slope will give you the direction of water. And so basically, there are some notations, mathematical notations to determine, to indicate which direction the flow is happening. So if your value is 1, then it means that it moves from my left to my right. If the direction is 2, then it moves diagonally down. If the value is 4, then the direction of flow is 4. So this is just a convention, okay, some notation where you store the direction as numbers. So now we can compute what is the steepest slope, and then from there we can get the direction of flow. So like that we compute for each and every cell and we get this flow direction grid. So your flow direction map will give you what direction the flow is occurring based on your steepest descent. So now you put it in terms of, so this is in terms of directions, in terms of arrows, and here you can represent it in numerics in terms of number notation that we had described earlier, 8 direction 4-point model. So now our job becomes easy. So since we know what direction water is flowing, we connect all the lines where water is flowing. So basically you go from your flow direction map to your grid network map. So now you start seeing your origins or initial beginning of stream network. So basically this cell is going to drain to this cell, and so you have a connect from here to here. This cell is going to drain all the way up to here, so it goes from here to here. So each cell you can kind of connect to the next neighboring cell based on your flow direction and get your grid network. So if I track this water, if I track a water that falls on my top left cell, so it's going to go all the way down here, and it is going to empty up to this point. So I know this is going to be my some kind of outlet. Now this is not my real outlet because I have taken an arbitrary square grid and I have computed the grid network in this one. So if I expand this and then compute what my flow accumulation is. So what my flow accumulation map will tell me is, it is going to count the number of cells that are going to drain into the current cell. So let's say we consider this top left cell. No cell is draining into this cell, so it is 0. Now if you consider the cell at the bottom, there are 3 cells draining into this cell. So one is here, one is from here, and then the other one is from here. So, and now if you consider this cell, 11 cells are draining. So this 3 plus 1, 4 is coming from here. These 3 are coming from here. This one is coming from here. These 3 are coming from here. So you have your flow accumulation number is 11. So systematically you can do these calculations and see how many cells actually drain into this cell. And so higher the number you get, more number of cells are draining into this particular cell. So you are kind of going downstream with higher numbers. Okay. So eventually you can get the largest number is going to be, sorry about this, so the largest number is going to be your watershed outlet, and your zeros are going to be your watershed boundary. So it has to be flipped here. Okay. So here in this case I have taken a square grid. So you have to really expand on the digital elevation map and look at if some other cells are draining into this. So if your flow accumulation number is 0, that means no cell is going to be draining into that particular cell. So that is a good potential for being a watershed divide. So you connect all your zeros. Okay. So in this case your 0 is in the boundary cell, so you cannot include the boundary cell 0. But if you have set of zeros in the interior cell, that will be your watershed boundary. Okay. And your maximum value will be your watershed outlet. So you can have some stream networks, you can develop stream networks based on your flow accumulation grid. So you can say that after about 20 cells drain into one particular cell, you can start forming some small streams, really minute streams. So you can set a threshold where you want to pick how many what is the smallest stream that you want to track. So if you say your flow accumulation number is about, your threshold is about 100, so you want to only track streams which are fairly reasonably in size, so that 100 cells have to drain into that cell to form a particular stream. So here there are some thresholds that have been chosen, okay, and you start seeing how your grid network or river network can be formed based on your digital elevation map. So, all this can be done using your geographical information systems framework, where you can do these math and calculations systematically and keep your geographical or spatial relationships on top of it and overlay it, and then get your watershed boundary and watershed outlet. So, here are some major watersheds in India. Okay. So, obviously people will know about your Ganges, your Narmada, your Brahmaputra, your Krishna, Godavari. Okay. These are your key watersheds, and so each one is colored, and your watershed boundary is being defined based on your flow accumulation grid. Okay. So, you get your boundaries for the watersheds, and your river network is also computed based on your flow accumulation grid. So here are another picture that talks about major rivers in India. So, I am going to leave at this. So, catchment annual water balance. Okay. So, basic is your influx equal to outflux. So, at an annual scale, let us say there is no rate of change of storage. Okay. So, if you talk about your fluxes, your influx is precipitation, your outfluxes are evaporation and transpiration. Evaporation is surface evaporation, transpiration is coming out through the plants, and your surface runoff, which is liquid water that is flowing on the surface, and your groundwater flow that goes deeper. So, now if you have precipitation information as an input, okay, so you have rain gauges, you have radar stations that provide input values for precipitation. Okay. And let us say we already know that groundwater flows are fairly small. Okay. In terms of magnitude, if you look at the global cycle, the groundwater fluxes are much smaller compared to the other fluxes. So, let us say we ignore groundwater flux. If we get some information about runoff, so for example, let us say we want to pick the runoff from Ganges. Okay. So let us say we want to get the annual flow out of the Ganges. So, I am just going to go to the first link, which is a Wikipedia. So, let us see, if we can see what the fluxes are. So, your discharge, average discharge is about 38 cubic meters per second. So, we can get some annual estimates for what your runoff will be for a particular catchment. So, let us say we delineate the Ganges watershed. Okay. Let us say we can get some precipitation data, spatial precipitation data, and we can see what the precipitation is over the Gangetic watershed. Okay. Now, we are going to ignore the groundwater flux. So, we have some estimates on what the runoff is. So, the runoff is about your watershed outlet is going to have your surface runoff, and so that is going to be some 38,000 cubic meters per second. So, multiplied by 365 days in the year. So, we will get some estimates for runoff. So, can we estimate what your evaporation and transpiration rates are? Okay. So, what do we get with this? So, what can we get from this? So, we will get some good estimates for your, so let me go back to your presentation mode. So, we can get estimates for what kind of water balance happens for different ecosystems. Okay. So, you have your desert ecosystems, you have your forested ecosystems, you have tropical savanna, you have different ecosystems, and each ecosystem responds differently. Your transpiration and runoff characteristics can change quite a bit based on if you have vegetation, what kind of vegetation you have, what latitude you have, what kind of precipitation you get, whether your precipitation is snow dominant or whether your precipitation is water dominant. Based on those things, you can get some indicator of how your evapotranspiration is in relation to your precipitation and runoff. So, some of the major ecosystems, at least in India, are forest ecosystems. So, you have your tropical rainforest, you have dry deciduous forest, which is kind of what we have here. So, we have a specific monsoon season, like a particular season where you have a large amount of rainfall, and then you have a dry season. So, based on this, you have something called a dry deciduous forest. So, quite a bit of the leaves actually shed during the summer dry months, and then once the monsoon starts, you have new sprouts. And there are broadleaf forests, evergreen forests and things, pine forests and things like that. If you go at higher latitude or altitude, you have tropical savanna and you already have deserts. So, I am going to leave this as a homework exercise. So, we can get some precipitation maps. I have some link for how to get annual rainfall. Okay. So, go play around, get some numbers, get a feel for what is the total precipitation in terms of how much is your catchment area, get some approximate numbers. Pick your favorite river, major river, and see what your runoff is, and how this evaporation and transpiration change. And then based on that, can you have some indication of what kind of catchment this is? Okay. So I'll stop here with some supplementary reading. So India has some Central Water Commission. They have quite a bit of information on water resources in India. There is also a very useful website, United Nations from UN, Water Facts. They have quite a bit of information, much more larger scale, what kind of water is used for agriculture versus what kind of water is used for irrigation and runoff and things like that. And then there is also FAO, Food and Agriculture Organization, which has some information, some useful information.